So today we're going to get some full gases unit review today. Basically, I'm going to go over pretty much every single concept that we covered in this unit. It'll be mostly example based today. So in other words, we'll post an example. I'll get you to try it on your own and then we'll go over it together. Anyway, here's today's plan. So like I kind of just said, we'll run through a whole selection of questions similar to what you can expect on the exam tomorrow. Keep in mind, the exam is only 15 multiple choice and 3 numerical response questions. So it is pretty short. We'll have a chance to ask questions early next class. It'll probably only take like maybe an hour to do the whole test. Excuse me. Now, these questions today that we're going to go over are in your notes booklet. They're starting on page 39. So if you haven't already gotten it out, make sure you have page 39 in your note package ready to go. That way you'll be able to follow through with these and not worry about copying them down. But anyway, let's get going. So first of all, formulas from this unit. We've worked with a ton of different formulas in this unit. You don't have to memorize them. They're on that green formula sheet I gave you in addition to the data booklet that we've already had. You can see them all there. There's a whole bunch. The first line of them was like from the first half of this chapter. The second line of them was from the second half of the chapter. What's kind of funny is that this one right here, we call this the combined gas law. It basically makes this one and this one completely irrelevant. Because if you know the combined gas law, if let's say your temperature, which is T1 and T2, if your temperature doesn't change from before and after you're using this, you can just ignore it because then T1 and T2 are the same thing, right? So they can just be ignored. Anyway, it is what it is. As for these other ones, there's the ideal gas law. That's this guy. Very, very important. This is only used for like when we were talking about gases right now. So there's not really a before and after. So if you're talking about like how a gas is right now, like if you're like, oh, I know the pressure is this and the volume's this, and I know the temperature, then how many moles do I have, right? You can use that. This one though, like the combined gas law, deals with a before and after, right? So there's the before, P1, V1, and T1, and then there's the after, P2, V2, and T2, right? Just if you really think about it that way, that helps kind of clarify when to use each of these formulas. So if you're talking about it right now, PV equals nRT, your ideal gas law. And if you're talking about a before and after, you're looking more at the combined gas law. Anyway, let's get rolling. So here's example one. I'll read it to you and then I'll get you to work on it on your own. A gas stored in a balloon under STP conditions. Remember, the exact values of STP are on your green formula sheet, which you can use here. So a gas stored in a balloon under STP conditions has a volume of 12.0 liters. The balloon is heated to 15 degrees Celsius. The pressure stays the same. Find the new volume of the balloon. Pause the video here, give it a try. All right, so I'm going to go over this one. Remember just a few minutes ago, I said like, oh, there's like those two formulas that are like totally useless once you know the combined gas law. This is going to be one of those questions where I show you why that is. Notice how this question is talking about before and after. So it's originally under STP conditions, and then it's heated. So there's a before under STP and an after once it's heated to 15 degrees Celsius. Well, the combined gas law says P1 V1 over T1 equals P2 V2 over T2. But notice the question also tells us that the pressure stays the same. Since the pressure stays the same, that means P1 and P2 are the same. You can just ignore them, right? Now this looks like Charles' law, where it says V1 over T1 equals V2 over T2. We're all good to go on that one, right? So again, I like using the combined gas law every single time. And then just if something stays the same, I just ignore that something in the formula, right? It'll work really well. Another thing that works really well once you have this is make a data bank. I know how silly that seems for some people, but it's a really good way of organizing your work. Let's start with V1. My initial volume in this case is at 12.0 liters. So I'll write that down. My initial temperature, T1, is the temperature of STP. In case you forgot what STP is, the initial standard temperature, ST, is 0 degrees Celsius. You don't have to memorize that. That is on your green formula sheet. So 0 degrees Celsius is my initial temperature. But wait, we don't like Celsius, not in chemistry at least. We have to change this to Kelvin. So to change to Kelvin from Celsius, you add 273.15. So 0 plus 273.15 is, of course, just 273.15 Kelvin. So there we are. V1 and T1, we're all ready to go. V2, on the other hand, your final volume, we don't know what that is. It says find the new volume. So that's our unknown. So we'll say it's equal to question mark. And then T2, your final temperature, is 15 degrees Celsius, which of course you got to change to Kelvin. So if you add 273.15 to that, you get 288.15 Kelvin. Now, we got our bank all worked out. I've kind of used a lot of room here, but I do have enough room in the corner just to finish this off. I'm going to just change color here. So if I throw these numbers into my formula, V1 is 12.0, so 12.0 over T1, which is 273.15, equals V2, which is what I'm looking for, over T2, which is 288.15. You can solve for V2 just by multiplying 288.15 on both sides. This gives you V2 equals, and you're going to have to round up here because we want 3 sig digs, 12.7 liters. So the volume really didn't change a huge amount when you just heated it to 15 degrees Celsius. But then again, that's only a 15-degree difference, right? So not really the end of the world. But it did go up, of course. When you heat a gas, the volume should increase. It should expand. So it is what it is. Anyway, example 2. The tire pressure warning triggers in my vehicle when the temperature drops below minus 20 degrees Celsius. That's actually true. It does. It drives me insane. If my tire pressure is usually 222 kilopascals at a temperature of 20 degrees Celsius, find the pressure at negative 20 degrees Celsius. Assume the volume of my tires stays constant. Pause the video here. Give this one a try. All right, I'm going to go over this one. I'll take the same approach as last time. P1 V1 over T1 equals P2 V2 over T2. That's your combined gas law. But wait, the question says your volume stays constant. So guess what? I can just ignore my volume altogether in this. So what this does is it just gives me P1 over T1 equals P2 over T2. If you want to make a data bank, probably a good idea. I'll try to write it smaller this time. P1, the initial pressure. I'll say the initial pressure is under like the 20 degrees Celsius conditions. So 220 kilopascals. And then T1 is 20 degrees Celsius. But let's be honest here, that equals 293.15 Kelvin. Now, P2, on the other hand, my final pressure, that's what I want to find. So I'll say question mark. T2, the final temperature, was that minus 20 degrees Celsius. So negative 20 degrees Celsius, but again, changing it to Kelvin, just add 273.15 to it, you'll get 253.15 Kelvin. Now I can throw those numbers into my P1 over T1 equals P2 over T2 formula. So P1 is 220 over T1, which is 293.15, equals P2, which is just P2, over T2, which is 253.15. To get P2 by itself, we just need to multiply 253.15 on both sides. So this gives me P2 equals, and I'm going to have to round quite a bit up here because it's like 189 point something. I'm going to round right up to 190 kilopascals. So notice in that final pressure that I just boxed, it certainly is a lot less than the 220 kilopascals that it usually is at a more comfortable temperature of 20 degrees. So no wonder when it gets really cold in the winter, my tire pressure drops considerably. So the sensor in my vehicle goes, "Hey, your tire pressure is really low. You must be getting like a flat tire or something." Well, I'm not. It's just really cold outside, and because of the combined gas law, it lowers the pressure in my tire because the volume did not change. It's unfortunate, but that's just how it works, right? Anyway, moving on. Example 3. Suppose you burned 5.0 liters of ethane gas, which is C2H6. Predict how much oxygen would be needed for this reaction and how much each product is produced. Okay, pause the video here, give it a shot. All right, I'm going to go over this one now. This is a bit of a funny one. Since we're predicting how much of like oxygen and the products are going to be made here, this tells me I need to start by getting a balanced chemical formula. So my balanced formula here is going to be my ethane gas, which is C2H6. It's burning, so I'm going to be combining it with O2 gas. And whenever you burn a hydrocarbon, that's just something that has carbon and hydrogen in it, of course, it's called a hydrocarbon. Whenever you burn a hydrocarbon, you're always given two products, CO2 and H2O. And of course, both of those are gases, carbon dioxide gas and water vapor gas, right? Anyway, we need to balance this. So one thing that you might feel like you need to do right off the bat to balance this is say, hey, well, I got 2 C's and I got 1 C. Maybe you'd put a 2 here, and then you go like put a 3 here to make 6 H's. But then you've kind of like hooped yourself here because if you have 2 of O2s, that means we have 4 oxygens plus 3 oxygens. So we have 7 oxygens in total. There's no way we can get a 7 out of like O2 here. Like, I mean, you can go 3.5, but it doesn't work that way, right? So we have to go back to the drawing board to balance this properly. You'll have to actually just double all that. So I'm going to say that it's going to be 4 of these. And then that means I'd have to have, you know, hold on. So 4 of these, that means I'll have to have 2 of these. Sorry, I'm just kind of getting rearranged here. 2 of these. So now those match. Now we have 12, 12 hydrogens. So we need to get 12 hydrogens over here. So I'll put a 6 here. There we go. Now I'm getting a little more oriented. 4 times 2 is 8. 6 times 1 is 6. 8 plus 6 is 14. We need 14 oxygens here. Well, that's just a 7 that's going to go there. So that's now balanced. I've got that one good. That was a bit of a tricky one. Now, for the rest of this question, it gets a little simpler once you understand that these numbers out in front actually represent how many parts of each are produced. So what this really means is 2 parts of ethane plus 7 parts of oxygen are going to make 4 parts of carbon dioxide plus 6 parts of water, which is kind of funny. You wouldn't think when you burn a hydrocarbon that you're going to get more water out of it than carbon dioxide, but in terms of molar amounts, it's actually true, you will. So the only thing we know here is how much ethane gas is being burned. We know that this 2 parts right here is actually 5.0 liters. So 5.0 liters is 2 parts. We want to find how much oxygen, carbon dioxide, and water gets produced. We just use our parts, right? Since 5 liters is 2 parts, just divide that by 2 and you'll find that 2.50 liters equals 1 part. So with this 1 part of 2.5 liters, we can figure out how much of the rest we have. Well, for 7, we would just go 7 times 2.5. That gives us 17.5 liters for our oxygen. Now, what's kind of dumb in this question, and I think it's maybe a little open to interpretation, but remember, since this is a science class, we have to use like the proper number of sig digs in our answer. Technically, this question only has 2 sig digs. So as much as this is uncomfortable, I think technically we're supposed to round this up to 18 liters, which seems really dumb to me because let's be honest, like we can see 17.5 liters, but it's just how it works. So whatever, but either way, 18 liters is what I'll say. I just went 2.5 times 7 to get that, by the way. As for this one, 4 times 2.5, that one at least gives us a nice even 10 liters right on the nose. So we got that. And then for this last one, 6 times 2.5. Hold on, actually, I didn't actually type that one down before. 6 times 2.5. Oh, that gives me, thank goodness, a nice solid number as well, 15 liters. So it's just this one that's kind of weird. 17.5 liters is the true answer. But if we have to go by sig digs, I have to round that to 18 liters, which is really dumb, but it is what it is. The bottom line is make sure you know how to do these kinds of questions. Because we're trying to predict how much of something is made or used, we have to get a balanced chemical equation first. Anyway, moving on. Example 4. I quite like this one, actually. It's a bit of a beefy one, but bear with me on it. Find the pressure of 400 grams of chlorine gas in a 750 milliliter container at a temperature of 290 Kelvin. Before you try it, the fact that I'm giving you a mass here is kind of funny. We don't deal with mass very often, but we do deal with moles quite a bit. Is there any way to turn mass into moles? Think about that one. Give this question a shot. I'll go over it when we unpause. All right, I'm going to go over this one now. Here's just a little bit of background. The little hint I was giving you here about mass, it's actually quite important to understand that in the gas unit, if I ever give you a mass, that is like 99% of the time meaning that you're going to have to bust out your molar mass. Remember, your molar mass is the stuff that you can find on the periodic table. So if you look in your data booklet, like that big printed booklet that I've given you, the molar mass is that big number in the top right-hand corner on the data booklet that I give you guys. So you're going to have to use that and then tie your mass to your molar mass to figure out your number of moles. Number of moles is very, very important in this unit. Another thing that you have to understand in this question is this is just talking about like a right now kind of situation. What I mean by that is this gas is not changing its temperature or its pressure or its volume. It's just right now it's in a container, a 750 milliliter container at a temperature of 290 degrees Kelvin. There is no before and after. It is just how it is right now. And when you're talking about a right now kind of situation where there isn't a before and after, it's just the formula PV equals nRT. That's called the ideal gas law, right? With those two things in mind, let's see if we can tackle this. PV equals nRT is the formula I want to use. Do we know our pressure? Well, no, that's what we want to find. So P is question mark. Do we know our volume? Yes, we do. 750 milliliters, but I hate milliliters. Let's turn it to liters instead. That's 0.750 liters. Much better. Do we know our number of moles? No, we do not. That's another hint that we'll have to change our mass to something because we don't know our number of moles. Do we know R? Well, we always know R. R is a constant. It's 8.31, like every single time. So that is on your green formula sheet as well. And then T for temperature, do we know it? We actually do, 290 Kelvin. And it was very nice of them. They actually gave it to us in Kelvin. Usually we have to like do the little conversion, which is dumb because it only takes like 2 seconds. It's just kind of a pain to add 273.15. Anyway, I'm rambling. So in order to use PV equals nRT to find our pressure, we need to find our number of moles first. The number of moles can be found if you have your mass by making a little trip to the periodic table. Chlorine gas, the formula for chlorine gas, because it's part of Hofbrinkel, those diatomic elements, chlorine gas is actually Cl2. Now, if you look at your periodic table, a single Cl has a molar mass of 35.45 grams per mole. But because it's Cl2, we have two of them, we have to just multiply that by 2, and you're going to get 70.90 grams per mole. Now, the molar mass that we got there is really useful because it allows us to convert grams to moles or vice versa. Let me show you how. I'm just going to do it over here. So 70.90 grams per mole. The units on grams per mole kind of tells us what the formula is going to be. It's going to be some number of grams, which we actually know, it's 400 grams, over some number of moles, which is what we would want to find. So I'll call it N. If we're trying to solve for N, we just need to do a bit of a switcheroo. It's really, really annoying when you're solving for something on a denominator. But to solve for N, I would multiply by N to the other side. So watch this. I'll multiply it over. So I'll put it over here. And then I'll divide by the 70.90. So N equals 400 divided by 70.90. And if you throw that in your calculator, you're going to see that N equals, and keep as many decimals as you're comfortable with, I'm keeping them all, 5.641748,942. Now that's overkill. You don't have to keep that many decimals, but as long as you keep at least 4 of them, it'll be more accurate that way. Now, what are we going to use this for? Well, if we go back to our drawing board here, remember we were trying to find our pressure, right? Since we had everything except for pressure and our number of moles, we weren't able to use the ideal gas law. But now we know our number of moles, so we can, right? So going back to PV equals nRT, I'll even write the formula again just so you see what I'm doing. PV equals nRT. How about I even change pen color so it really sticks out? My pressure is unknown. My volume is 0.750. My number of moles is, buckle up, 5.641748,942 moles. R is 8.31, and then T is 290 Kelvin. We want to get pressure all by itself, so I would multiply all 3 of these numbers right here all together and then divide by 0.750. So my pressure that I got before I do my sig digs is about 18,128. But we don't like that. We need to have 3 sig digs, as you can see in our question. So if I turn this into a 3-digit number, just keep my first 3 digits, and I won't have to round up because the 2 just rounds this down, keeps it as a 1. So it'll be 1.81, right? This is scientific notation. So first digit, 1.81 times 10 to the, count how many places your decimal would have to move over. 1, 2, 3, 4 places. So 1.81 times 10 to the 4. And this is pressure. So the units will be kilopascals. Very bulky question, but I actually do kind of like it. It's really important that we understand that mass in the gas unit does not really stand on its own. Molar mass is going to be the key that allows you to change it to moles. To find the molar mass, you have to make a trip to your periodic table. We got one more question to do here. This one will go a little quicker, hopefully. Example 5, find the mass of a sample of ozone gas, which by the way is O3, that occupies a volume of 4.00 liters under SATP conditions. There's a couple ways you can do this question. Pause the video here, give it a shot. All right, so once again, we're looking for a mass this time, just like before, even though we weren't given it. When you're looking for a mass, or when mass has anything to do with the question you're dealing with, chances are you're going to have to deal with your molar mass. So that might be somewhere we could look at first, or maybe we could wait a moment. It is what it is. But just put that in the back of your mind for a moment. Molar mass is probably going to come around. Now, the other thing that comes around here is this is not a before and after question. This is a right now question. And again, what I mean by that is it's not saying that we're heating up or pressurizing or changing the volume of this ozone gas. We're just talking about how it is right now. We're just looking for how much its mass is, given that it occupies 4 liters under SATP conditions. And remember, SATP, according to your data sheet, is 25 degrees Celsius and 100 kilopascals. But then there's something else with that. It's called a molar volume. I'll talk about that in a second. But anyway, since this is a right now question, you could, in theory, use PV equals nRT. Now, with PV equals nRT, if you solve for your number of moles, you could then jump to your molar mass and solve for your mass. Nothing wrong with that at all. I would imagine some of you probably actually did do that. But there is a quicker way. Under SATP conditions, we have something called a molar volume. What this means is under SATP conditions, no matter what kind of gas you have, it doesn't matter if it's ozone gas or water vapor or carbon dioxide or hydrogen or whatever, no matter what kind of gas you have, the molar volume under SATP conditions, according to your formula sheet, is 24.8 liters per mole. What that means is 1 mole of gas under SATP conditions will occupy 24.8 liters. That's what that means. We can actually use this relation, just like we use our molar mass, to find either our number of liters or our number of moles. Excuse me. We already know our number of liters. So in other words, I can use this little thing right here to find my number of moles. Watch what I'm going to do. 24.8 liters per mole, which I know I can use this number because it told me we're in SATP conditions, equals my number of liters, which is 4.00 liters, over my number of moles, which I'll just call N. Just like before, to solve for N, we need to multiply it over to the other side and then divide by 24.8. So N equals 4.00 divided by 24.8. What this is going to do is it's going to give me in my calculator, N equals 0.1612903,226, and that's my number of moles. Now, why do we care about that? Well, the number of moles can help us find our mass. That's ultimately what we're trying to find here. And remember, anytime in a gas question that you're looking for your mass, your molar mass is going to be involved. Let's now find our molar mass of oxygen. How about I change color again? Let's use a different color. Let's use green this time. The molar mass of oxygen, or rather ozone gas, O3, is going to be 3 times the molar mass of oxygen, which is 3 times 16, according to your periodic table. Well, 3 times 16 is 48.00 grams per mole. Now we're just about 1 or so steps away from getting this done. From this molar mass, 48.00 grams per mole, we can set this equal to some number of grams. I'm going to change that G, it looks terrible there. Some number of grams over some number of moles. Well, that's what we want to find. We want to find our number of grams. So I'll call that X for an unknown number of grams, over a number of moles that we have, which is this number right here. So over 0.1612903,226 moles. Quite a mouthful, but it is what it is. So long story short, we can take our molar mass of 48.00 grams per mole and just multiply over our number of moles. This gives me X equals to just 3 sig digs, 7.74 grams. And that right there is my final answer. A lot of work with these, right? The moral of the story is here, and I know I've said it a few times, if you are ever given a mass or even asked to find a mass, you are probably going to have to use your molar mass. So you're going to have to make a trip to your periodic table. There's not really anything else in the gas law or gas law unit that gets around that. Anyway, so for practice, any of the many worksheets or handouts that you've been provided would be wise. There was a gas law unit review one that had like a picture of a cat on the front of it. That would be a good one. You also received one last class that was called like Chemistry 20 practice questions or something. That would be another good one. If you'd rather make like a study guide or something on your own, or if you'd rather just parse through your unit booklet, that's up to you, whatever you need. If you look back at any of your old quizzes, that could also be a good resource if you wish. The gases unit exam tomorrow contains 15 multiple choice questions and 3 numerical response questions. It shouldn't take much more than 1 full block. So I'm going to give you the first at least 15 or so minutes to prepare on Wednesday. If you have any questions, of course, make sure you're reaching out. You can send me an email, whatever you need to do. Best of luck.